Okay, today we're going to talk about reactions of epoxides with carbon nucleophiles. And then if there's time, we'll move on to neighboring group participation. So we've already been using one carbon nucleophile in this class, and that's the deprotonated acetylide. And we've been using it to do SN2 reactions with alkyl halides. Now, what we are going to be doing is also reacting them with epoxides, because epoxides also are SN2 electrophiles. Now, there's going to be a little bit more specificity in these reactions that I'm going to actually ask you to highlight what solvent to use. In the first case, with the reaction of that with the bromide, I didn't really care about what solvents you used. In reality, the solvents you typically would use for deprotonated acetylides is something like diethyl ether. And we'll use that for epoxides as well. And so the nucleophile attacks, it's a basic nucleophile, capable of doing SN2 and E2. Epoxides have a tendency to just do SN2 reactions. And since it's a basic nucleophile, the acetylide is going to attack from the less hindered side. Giving this molecule here. And then to finish up the reaction, after we've had all the acetylide add to that, what we're going to do is add to the flask a little bit of acid and water. H3O plus is what's called an acidic aqueous workup. What that H3O plus actually is, it's not a bottle of H3O plus, but what it usually is maybe some ammonium chloride, about 10% ammonium chloride in water, or it could be 1 molar HCl in water. It's just whatever is on the shelf that's handy. Point is, it's a weakly acidic solution. We're not being very specific what it is, but it's just, you think of it as acid and water. Now, the reaction, the initial epoxides start out as optically active. Again, during the mechanism, the entire process stays chiral, so it's still optically active. Okay. A couple things I want to point out. The nucleophile and the proton source are in separate steps. They are not together at the same time. This is vitally important, because the issue is, say you had reaction of an alkoxide in ethanol with the epoxide. The product is this. Here the nucleophile and the proton source are together in the same step. And by step, I mean synthetic step. And this is perfectly acceptable, because if the base, the nucleophile, takes the proton off of the solvent, you get the same result. But if we tried it with something like this, the epoxide, the product that we would get would be this. And not that. Because acid-base chemistry is very fast, and the moment you put this in the protic solvent, you have that acid-base reaction. This has a pKa of 15. This has a pKa of 25. Reaction is heavily weighted to the right. And so, when you throw this in a protic solvent, what you end up doing is you end up deproting the solvent. And this is the new nucleophile. So that's why when doing acetylide chemistry, or these carbon nucleophiles that are strongly basic, you need to have the nucleophile and the proton source in separate synthetic steps. With the nucleophile being in an aprotic solvent, like diethyl ether, and then the proton source coming afterwards. Okay. Now, so these are carbon nucleophiles. We've done acetylides. Let's talk about a new carbon nucleophile. Grignards, organolithiums, and cuprates. And I'm going to underline cuprates because they are the best at doing this type of chemistry. But what these are a different type of carbanion where the carbon does not need to be sp hybridized. It can be sp2 or sp3 hybridized. And the only difference between these is what the counter ion is. In a Grignard, say ethyl Grignard, it looks like this. Or it could be this, or it could be this. Where the key is, you have a carbon-magnesium bond, and then the magnesium is also bonded to a halogen, like a bromine, a chlorine, or an iodide. Organolithium is much simpler than that. It's basically a carbon bonded to a lithium. The cuprates. These are a lot more difficult, so we're not going to worry about this, have you memorize the structure of these cuprates. But the cuprates that typically are used look something like this. But all of these, what they essentially are carbanions. So, how to make these? We'll worry about the cuprates a little bit. Let's talk about making the Grignards and the organolithiums first. So the way to make a Grignard is you take a bromide or chloride or an iodide and you treat it with magnesium metal in ether. You can get either the magnesium chloride, the magnesium bromide, the magnesium chloride, or the magnesium iodide. Iodide works best for the reaction. But it's the most expensive. Chlorine is the cheapest. But it is the least reactive. So a vast majority of Grignard reagents use the bromine. Because what the bromine does is it balances cost with effectiveness. But in this class, we're not worried about the cost, so any of these things will work, and we'll accept any of them. Organolithiums. You essentially take, again, any of these things. Not magnesium. Chloride, bromide, or iodide, and you treat it with lithium metal and a suitable solvent like and you get an organolithium out of it. And you can use any of these as well. With the same thing of iodine works best, chlorine works the worst, but bromine is the one that's usually used. Okay. The mechanism of this is a radical mechanism called a single electron transfer type mechanism. We're not going to worry about that. You don't have to worry about this mechanism for this course. Reactivity-wise, and I'm just going to use MgBr for Grignards. Know what applies to MgBr also applies to MgCl and MgI. These molecules are very, very strong bases. Because essentially, these molecules are somewhere in between ionic compounds and covalent compounds. These molecules have quite a bit of carbanion character to them. And the conjugate acid of these is simply an alkane. And alkanes have a pKa of 45, so these have a conjugate pKa of 45. Ridiculously strong base. So there's some restrictions on what you can put on organolithiums and Grignards. One of which is they cannot contain an acidic proton because they themselves are strong bases. By acidic proton, we're looking at OH, NH, SH, or a terminal alkyne. Because all of these would end up deprotonating this alkyne, or this SH, NH, or OH. So R can't contain these. These also react with epoxides, and carbon X pi bonds. What I mean by this is they can react with nitriles, carbonyls, imine type species. So these types of things cannot be present on the R groups. That means molecules like this is an illegal organolithium because it contains a carbonyl. Now the reaction of a Grignard and organolithium with carbonyl, that's covered in Chem 345. And so I wish it was in Chem 343, but alas, it's in Chem 345. So we're not going to talk any more about that other than you can't have these present. And there is one last thing about Grignards and organolithiums that you can't have present. You cannot have leaving groups on the alpha or beta carbons, even bad ones. This is an example of an illegal organolithium, because essentially what this is a carbanion. Here's the alpha carbon, here's the beta carbon. It's got a leaving group there. That carbanion goes there, and this molecule instantly becomes an alkene. And the leaving group doesn't even have to be a good one. It can even be an oxygen one, which is a poor leaving group in a lot of situations. But since this carbanion is so darn basic, it can actually kick that off. So you don't want an oxygen or a halogen on the beta carbon. You really don't want one on the alpha carbon as well. Because what this does is this becomes what's called a carbene. And carbenes are another type of compound that we'll talk about later on this semester. But this particular carbene gives a mess. So there's the rules and restrictions. Now let's talk about how to apply this. Let's take this molecule right here. We can treat it with magnesium or lithium. If we treat it with magnesium, we get a Grignard. And then what we can do with that Grignard is we can react it with an epoxide. Now, since this is a very basic nucleophile, much more basic than even an acetylide, we definitely need an aprotic solvent, like diethyl ether. And then we add this. Okay. So the product we get after this first step, and let's actually separate out these steps, is we get this R group right here. And let's number it. 1, 2, 3. 1, 2, 3. And 3 is the nucleophilic carbon. And it's going to attack the electrophilic carbon. And it doesn't matter which side it attacks because the two sides are equal to each other. So it attacks carbon 4. So we create a new bond between carbons 3 and 4. Carbon 5. And carbon 5 gets the L minus, because essentially what's happening is these electrons going to this carbon, and that's kicking the electrons up onto that oxygen. Then we add H3O plus. And we get our alcohol. Okay. And organolithiums can do the same thing. Now, the moment of truth. Grignards and organolithiums react cleanly with very few epoxides. This has to do with the reactive nature of Grignards and organolithiums and the counterions of magnesium and organolithiums. cuprates are far better at reacting cleanly with epoxides. So if you wanted to do a little bit more complicated epoxide, you need to use the cuprate. So how you go about doing that? You can use Grignards or organolithiums. I'm going to start out with the lithium. So you have the organolithium. And what you do is you add it to your epoxide. We'll make this an optically active epoxide. In an inert solvent like ether. And to make the cuprate, you just throw in some copper cyanide. Think of copper cyanide as the special ingredient that makes the reaction actually work. We're not going to go into the structure and the exact mechanism of the cuprate, but you can just basically add copper cyanide in to a reaction involving an epoxide, and you end up performing the same reaction as up above. Only in this case, it's a lot more complicated. 1, 2, 3, 4, 5. So again, we have the 3 carbons. 1, 2, 3. The nucleophilic carbon is carbon 3. That's going to be attached to one of the 2 alpha carbons. Here, the 2 alpha carbons are different. We're using a very basic nucleophile, so the alpha carbon that's attacked is a less hindered one. That's carbon 4. So that's going to be carbon 4, like so. And then that wedge is going to be up. And then carbon 5 is the one that's attached to the O-. And then the 2 methyl groups. And this stays optically active. And then you protonate. And that protonation step is a separate step that you have to add the H3O plus 2. Okay. So if we were to write this out another way, starting with, say, let's throw the epoxide out here. Optically active. And we treat the epoxide with the organolithium, copper cyanide, and ether, followed by H3O plus. Product that we get is this product right here. And it's optically active. Okay. Now, to show you something neat, confusing, and important. It's an SN2 reaction, so the alpha carbon is inverted. So, if we take a look at the alpha carbon that was attacked, that's that carbon right there. We figure out R and S on it. 1, 2, 3. That's an R chiral center. We find that chiral center right here. We figure out R and S on that. 1, 2, 3. That's an R chiral center. R stayed R. Even though the R chiral center stayed R, this alpha carbon was inverted. I'll give you a little bit moment to stop cursing while I drink my Dr. Pepper in smug satisfaction. And let me show you. Say we have this molecule here. So essentially we're reacting the epoxide with ethoxide and ethanol. Well, ethoxide adds from the less hindered side. And we get this mechanism right here. And then we protonate. Like that. If we figure out R and S here, 1, 2, 3, that's an R chiral center. 1, 2, 3, that's an S chiral center. Here, the alpha carbon obviously inverted. By this mechanism. If we use the mechanism using the carbanion, all we're doing is swapping out a C minus for an O minus. And then it's protonated by the acid in the water. Now, the reason why when you use the organolithium, the R stays R, and when you use the alkoxide, the R stays S, has nothing to do with the reaction itself. It has to do with how you calculate R and S. Remember, R and S is purely an artificial thing that we use. Nature doesn't use R and S. It's based off of the priority. And normally, when you do it, the nucleophile has the highest priority. In all the SN2 reactions we've done before, the nucleophile at the end had the highest priority, and the leaving group had the highest priority. And so you're switching those two. But if you take a look, when we're dealing with an organolithium, sometimes the nucleophile doesn't have the highest priority. And that's what happened here when you're calculating it. Okay. So if you want to make sure that you inverted and you're using the R and S system, make sure that your nucleophile, no matter what the actual priority is, make sure your nucleophile has the highest priority. And so if you do that, make this one artificially 1, and this would be 2, and this is B3, then that's S. 1, 2, 3, that's R. This is just a way of making sure that you actually drew the structure correctly and it inverted. So, give you a second to think about that and curse some more. I just wanted to warn you about that. Okay. Now, Grignards, organolithiums, and cuprates do SN2 reactions on epoxides only. They do not do SN2 on alkyl halides, like normal SN2 reactions. What I mean by that, if you have a Grignard, and you have that, actually let's do an organolithium. Grignard's pretty much the same. Organolithium and that, in ether, you do not get that. What you actually get is a little bit more complicated and beyond the scope of this course. That's more of a topic for Chem 345. But I just wanted to warn you right here that you can do SN2 reactions when your nucleophile is an sp hybridized carbanion, but you cannot do SN2 reactions when your nucleophile is an sp2 or sp3 hybridized carbanion. Okay. Now, that's actually pretty much all I want to get through for today. And so we'll pick up neighboring group effects on Monday.